Okay, 21.65. A small 12.3 gram plastic ball is tied to a very light 28.6 centimeter long string that is attached to the vertical wall of a room. A uniform horizontal electric field exists in this room. When the ball has been given an excess charge of negative 1.11 microcoulombs, you observe that it remains suspended with the string making an angle 17.4 degrees with the wall. Find the magnitude and direction of the electric field in the room. Alright, so let's draw a free body diagram for this dude. He's got some gravity pulling him down. He's got some tension pulling him over. And he's being pushed away from the wall, so that means our force from the electric field is to the right. And it's a horizontal field, therefore it's a horizontal force, because that's how that works. Alright, so let's do the sum of our forces. In the x direction, we've got our Fe to the right, minus, that's our angle there, our tension, that's going to be sine theta due to the placement of the angle. He's not moving, so that's equal to 0. And Fe, we've got y direction, we've got t cos theta pulling us up, minus mg pulling us down, and I'm not accelerating, so that's also equal to 0. Alright, let's rearrange some stuff. So if I move my t sine theta to the other side, I've got t sine theta is equal to Fe. And if I move my mg to the other side, I've got t cos theta is equal to mg. So Fe, because we're dealing with a small point, we can approximate that as a point charge. So we can write that as QE. Alright, so now we're going to do that fun trick. Swoop! Divide both sides by each other. My t's cancel out. Sine over cosine is tangent. And then I have QE over mg. So if I solve for the electric field, I get mg over q tan theta. So the magnitude of my electric field is going to be mass, which is 12.3 grams. So it's 12.3 times 10 to the negative 3 kilograms. G is 9.81 meters per second squared. Q was 1.11 times 10 to the minus 6 coulombs, or negative, and tangent of 17.4 degrees. Alright, 12.3 minus 3 kilograms times gravity times tangent of 17.4, that is not a point, 17.4 degrees, divided by minus 1.11 times 10 to the negative 6, splat. Gives me an electric field of minus 34,066 newtons per coulomb. Alright, so this minus sign tells me that the field is in the opposite direction of the force that was drawn. So my force is to the right, my field is to the left. So my E field is 34,066 newtons per coulombs to the left. We can double check this because this is a negative charge. Negative charges move against the field. So if my charge wants to move to the right, that means the field is pointing to the left, which is what we got. Sweet.